Welcome to this video on analytical solutions of partial differential equations. By the end of this video, you will be able to solve PDEs using the method of separation of variables. Now, for some simple PDEs, we can actually find analytical solutions. And here is an example of a pretty straightforward simple PDE, about as simple as we can make it. And du dx plus du dy is equal to 0. Now we can solve this PDE analytically using what's called the method of separation of variables. And at its heart is the following solution ansatz. Right? We assume that the solution has the form u, which is the dependent variable, which is a function of the two independent variables x and y, is equal to a function uppercase x that depends only on the first independent variable x times another function uppercase y that depends only on the second independent variable lowercase y. Now, if we take this ansatz and substitute it into the PDE, what do we get? Well, we first have to take the partial derivative of u with respect to x. But x is made up u is made up out of the product of a function x of x and y of y. So this function y that's in the product is not a function of x, so we can pull it in front of the partial derivative. So du dx is equal to uppercase y times d uppercase x with respect to the independent variable lowercase x. Do the same thing with the partial derivative with respect to y. X, uppercase x, is not a function of y, so we can put it in front of the partial derivative. So we have plus uppercase x times d uppercase y, d lowercase y. And that is equal to 0. Okay, so let's separate the variables. Let's bring everything that is a function of x to one side and everything that's a function of y to the other side. So we have on one side, we divide by uppercase x, right? We have 1 over x times dx dx is equal to minus 1 over uppercase y dy dy. So everything that's a function of x is on the left-hand side. Everything that's a function of lowercase y is on the right-hand side. Now, we have that the left-hand side has to be always equal to the right-hand side, according to the statement here, right? But the left-hand side is a function of x, the right-hand side is a function of y. So whatever the values of little x and little y are, these two sides always have to be equal. And that can only be true if actually both sides are equal to the same constant c. So that means left and right-hand side have to be equal to c. So that means, well, the left-hand side has to be equal to c, okay? And let me solve this now, right? I can multiply by dx, so I get 1 over x dx is equal to c times dx. I can integrate this, right? I get the logarithm of uppercase x on the left-hand side, and for the right-hand side, I get c times x plus an integration constant c1. And I can solve this for my function x of x by taking the exponential of both sides. So I get e to the power c times x plus c1. That is my function uppercase x. But I also know that the right-hand side has to be equal to c, so these functions of y. So I have negative 1 over y times dy dy has to be equal to 0. We move the dy over to the right-hand side. I get minus 1 over y. dy is equal to c dy. When we integrate this, I get the logarithm of uppercase y is equal to the minus sign. I move over to the right-hand side. So minus c times y plus an integration constant c2. Let's take e to the power of both sides to get rid of the logarithm. So I have my function uppercase y of little y is equal to e to the power negative c times y plus c2. Now let's take those solutions for x of x and y of y and substitute this back into our assumed form of the solution u, back into our solution ansatz. So u of x and y is therefore equal to x of x, which is e to the power cx plus c1 times y of y, which was e to the power negative cy plus c2. And now I can combine these, right? I have the same c, so I have e to the power c times x minus y. And then I have e to the power c1 times e to the power c2, both of them being integration constants. So e to the power, that constant, is simply another constant. So that would then just be k, I can see constant k times e to the power c x minus y. And that's the solution, right, to this ODE. Now, the c and the k, they depend on the initial and boundary conditions itself. Okay, let's do another example, a little bit more complicated. Let's try to solve the following PDE. So y times du dx minus x times du dy equal to 0. We're trying to find the solution using the method of separation of variables. So let's start with the solution Ansatz. That just means the assumed form of the solution. So u of x and y is supposed to be equal to a function that's only a function of x times a function that's only a function of y. And if I do this with handwritten notes, it's going to be hard to tell an uppercase x apart from a lowercase x. So let me call the function of x alpha, so an alpha of x times a beta of y. Okay, that's my Ansatz. And I'm going to substitute this now. Substitute into the PDE. That's the next step. So I get y times, right, that's this. Now I have to take du dx, right, but beta is just a function of y, so I can move it in front of the derivative. So y times beta of y times d alpha dx minus x times, and now I have to take the partial derivative of u with respect to y, but alpha is only a function of x, so it can move in front of this derivative. So I have minus x times alpha of x times d beta dy, and that has to be equal to 0. Okay, now we're going to isolate all functions of x to one side and all functions of y to the other. Okay, so that would mean, let's see, what do we have in terms of functions of x? So we have here, if we bring this over with a plus, and then we have to divide by x times alpha of x. So we have 1 divided by x times alpha of x times d alpha dx. Right, that is simply this portion here, right? It's this guy and this one. And then I have beta dy, and these are the functions of y as well. Functions of y, functions of x. I have to bring them over to the other side, and so there's a minus, this becomes a plus. So 1 divided by y times beta of y times d beta dy. Now this here is a function solely of x. This right-hand side is a function solely of y. And for them to be always equal to each other, no matter the x, no matter the y, both sides have to be equal to the same constant c, which is a constant. Okay, so that means that 1 divided by x times alpha times d alpha dx is equal to the constant. So then let me bring the x and the dx over to the other side. So I have 1 over alpha d alpha is equal to c times x dx. And now I'm just going to integrate this, right? And I get as a solution that the logarithm of alpha is equal to 1/2 cx squared plus an integration constant c1. And to get rid of the logarithm, I take e to the power of both sides. So I get alpha of x is equal to e to the power 1/2 cx squared plus c1. Okay, so that's the left-hand side, the function of x. Let's look at the function of y. So this has to be true as well. So I have 1 over y times beta. The beta dy is equal to the same constant c. Let's bring the y's over to the right-hand side. So I have 1 over beta. D beta is equal to c times y dc. Let me integrate both sides. I get the logarithm of beta is equal to 1/2 cy squared plus another integration constant c2, and therefore beta of y is equal to e to the power 1/2 cy squared plus c2. Okay, so now these can now be substituted back into the ansatz. So the ansatz was what? U of x and y is equal to alpha of x times beta of y. And I found these now, right? So I have here my alpha of x. It's this function. And my beta of y goes into here. So this is then equal to e to the power 1/2 cx squared plus c1 times e to the power 1/2 cy squared plus c2. Okay, so let's combine these a little bit. So we have u of x and y is equal to e to the power c1 times e to the power c2 times e to the power 1/2 c x squared plus y squared. And let's call this here with these two constants c1 and c2 that can be combined into a single constant k. So therefore our solution here is u of x and y is equal to k times e to the power c divided by 2 x squared plus y squared. That is the solution to this PDE, and we could confirm this. And if you do these kind of calculations and you want to confirm your result, what you'll have to do is take this function here and substitute it into the original PDE, and that function will solve, in this case, the PDE itself. Thank you for watching.